We have a lot to cover today. Thursday, we have an exam, our first midterm exam. Um, and I'm going to go over a few reminders right now with you concerning it. And then we're going to get into the Newton's third law and everything. So let's focus on exam one. First of all, first comment, we're going to have two homework assignments tonight. One of them is a review assignment and one of them is a regular assignment. The regular assignment is homework 5. The review assignment is called Mini Review Set 1. And they're both set to activate at 1:20 at the end of class today. So you're going to have plenty. I know you're going to want to study, so hopefully these will be good study tools. By the way, the get your studying in on the mini review before Thursday morning. I've set it to deactivate at 9 a.m. So that's a little bit sooner than usual. The homework will be due at 12:01, but the mini review set 1 for you guys will go off the air at 9 o'clock. And you'll be able to see that in web courses. All right, about the test itself. It is a 50-point test, as I wrote in the syllabus. There will be about 45 Scantron items. Now, what you want is one of these raspberry colored Scantrons that you can get at the bookstore. You can get them at the SGA office in the student union, supposedly. Vending machines and whatnot. Although the vending machine on this floor apparently is out last time I looked. There's going to be 45 Scantron items, and then there's going to be 3 iClicker items. And that'll be on the last page of the test. The iClicker items, I can tell you what they are right now. There's 1 multiple choice and 2 calculations. Each of the calculations is worth 2 points. And the multiple choice clicker question is 1 point. Total of 5 points. So 50 points total. Scantron items are 1 point each. And so get your Scantron now. Basically, make sure that you bring a calculator. You may not use your cell phone calculator. You may not use your cell phone for any reason. Okay, so if I see you're using your cell phone, I'm going to assume you're trying to cheat, and I'll take your test and give you a 0 on it and maybe get you booted out of campus, which we've done before. So don't do that. Anyways, get a regular old calculator. And if you forget it, if you blow it and you forget it, there should be sufficient time to do a couple calculations with 5th grade long division and stuff like that. So you'll be all right. But if you have a calculator with a square root key, you're good. Okay, the Raspberry Scantron, and there's something I want to point out to you. On the Raspberry Scantron, you in the area that says ID number, you have to put your PID. All right, now your PID, for those of you that are newbies here at UCF, the PID is the first letter of your first name, and then your UCF ID number, which is 7 numbers. And if, I had a student come up after class, Dr. P, what's my PID? Well, it's going to look something like this. This is one I just made up, phony one. And you bubble in the numbers for it. But a PID and your NID, I think your NID has 2 letters in it to start, and then a bunch of numbers. And the PID has 1. And if you're a new student here, a transfer or a freshman, and you didn't realize that, my first semester here, I went until about Thanksgiving before I finally twigged to the fact that, yeah, there's a difference between a PID and an NID. I was so screwed up with all my paperwork and everything because I couldn't figure out, the difference. Anyways, try to remember it, and you're going to have to bubble that in on your form. What do you bubble it in with? Good old number 2 pencil. All right, get a good one and a good eraser. The eraser is important because you don't want to cause smudges on your test. I see guys doing Scantron exams with ink, but I don't know, man. I would never want. I mean, I'm the instructor, and I wouldn't want to do that. And then finally, bring your iClicker 2, as I've mentioned. That'll be the last thing on the test. Now, about the PID, one more thing. The PID, if you don't fill it in, you're going to be on my bad boy list. And the bad boy list is also known as the headache list. Because if you don't put your PID on there, I got to go through the entire pile of 600 Scantrons, a pile of Scantrons that are not alphabetized, and I got to find yours. And so I'm going to be a little bit if I have to do that. And see, I'm going to remember your name. So you're automatic, even if I don't even write down the bad boy list, you're going to be on it just because I have to track you down. And the other thing I have to track you down for is the test form, which you're going to have to bubble in of an A, a B, a C, or a D. All right, so if you avoid, or if you bubble in your PID and bubble in your test form, you're going to avoid giving me a headache, and that's going to avoid getting your name on the infamous headache list. And so try to remember that. And I'll nag you some more about it on Thursday. So if you forget about it, hey, Dr. B, aren't you going to nag us about PID? Go ahead and remind me to do that on Thursday if I don't do it. Now, one thing you want to do in addition, and I didn't put this in the slides or anything, the normal pace. When I first got here to UCF, I never did Scantrons very much till I came here to UCF. And so I asked my boss, the chairman, how many am I supposed to do on a regular midterm? And he said, well, I budget 1 minute for each question. And that's usually pretty good. Now, we've got 80 minutes for this test. We start at noon. We finish at 1:20. And we won't get to the test. I won't turn you guys loose to start the test until maybe 12:05. But that's still 75 minutes. And it's roughly going to be about 50 Scantron type questions. Now, some of them you'll go through fast. Some of them you'll have to really think. And there'll be 2 calculations, deluxe calculations in the clicker section. So those will take a little bit of time. But hopefully, the sooner you can get here and get into your chairs, the sooner we can start the test. Also, for this class, I want you all to come sit in the first let's see. Okay, young lady with the green top over there. Can you raise your hand? Okay, which row are you in? Let's see, 1, 2, 3, 4, 5, 6, 7. I want you to try to get into the first 7 rows in the middle. And the reason I do, so make sure you take a shower before you come to class so you don't smell up your neighbors. And just be ready to roll, have everything ready, and get down here to the first 7 rows. And we're going to herd you into the first 7 rows if you don't do it. But get into the first 7 rows, sit anywhere in the front, all the way back to the 7th row. And then I'll be able to hand out the tests really fast. And handing out the test really fast means you get to the test really fast. And if you get to the test really fast, you get as many of those 80 minutes as possible. And believe me, you are going to want every single minute that you can get. All right? And if somebody causes things to slow down, it's not going to be happy. All right? So get here at noon and get down to the first 7 rows and squeeze yourself in somewhere, or get here early, and that'll be good. And we'll get started fast. Another question students are typically worried about and ask me about in web courses, messaging, also in office hours and stuff. Dr. B, how should we memorize the formulas, or are we going to have a formula sheet? And I believe I've mentioned this before, but what we normally do, and go ahead and get your clickers ready because we're going to do these questions together. Normally what I do is I set up the first several items on the test, a set of formulas, and then a set of concepts. And your job is to match a formula to a concept or vice versa. And so, for instance, this set of formulas over here, A through D on the right side of the screen, that's actually the equivalent of a formula sheet. But I have these, let me go back. I have these tips over here, and these are the things that you have to match. So you have to match concept 1 to one of these formulas, concept 2 to one of these formulas, concept 3 to one of these formulas. All right? And what we're going to do right now is work those out. We're going to work out 2 of these items, number 1 and number 2. And let's start that right now. Now, if you are a student that has not used your clicker before, hold the power button until the square flashes in the upper left of the display, and then type in A and then A again, and you'll get the go nitro and then the ready symbol. All right, now here's question number 1. You can go ahead and start voting. A, B, C, or D. Which one's the definition of acceleration? 20 seconds. Five seconds. 4, 3, 2, 1, 0. My little track phone. I dropped my iPhone a couple weeks ago, so I'm stuck with this little track phone. Okay, let's go to question 2. We'll go over the answers in just a minute. 30 seconds. Newton's second law. Fifteen seconds. Now, on the clicker questions on the exam, 5, 4, 3, 2, 1, 0. The clicker questions on the exam, you'll have them printed out on the last page of the test, so you'll be able to go through it at your own pace. And I'll have the instructions for you printed there about how to go from question 1 to question 2, how to type in the answer, and it works really nice. And you'll be able to go back and forth. You know, like right now, nobody can do number 1 again, but on test day, you'll be able to go back to number 1 and change your answer if you think it over again. All right. Now let me ask you this. Which of these is Galileo's new state of motion, or describes Galileo's new state of motion? I'm not going to click this. I'm not going to start this question because I blew it in the first hour. And I want to keep you guys the same number of questions as the first class. Who wants to hazard a guess as to which of these is the correct match? Okay, brown shirt in the aisle. Yeah. E? D for Delta? That is correct. Here's the answers, you guys. Go ahead and jot that down. And this is similar to what you'll have to do. I mean, the test form itself will look different, but basically it'll function in this way. And your homework tonight, you have review set 1, and it's got a little tiny matching exercise as well. All right, so the review is going to, that review set is going to help you with that. Notice that I haven't got a question for answer B. B for Bravo. Ooh, Jeopardy, physics Jeopardy. For 400. Y of t equals 1/2 gt squared. What's the Jeopardy? Drop distance, incorrect. Distance triangle, okay. Better answer? Incorrect. For the daily double, in the back. Weight force is in here, but that's not the best answer for this. Yes? Free fall is related to this. But you know what this is? Okay, what is it? Parabola. Oh, you're burning up. Go ahead.
Ballistic arc on Earth.
Ballistic arc on Earth, parabola. You're burning up, but this is not the parabola. This is the y coordinate on the ballistic arc, which is a parabola because of free fall on the planet Earth. All right, so you know what? That gives me an idea. You know, the SI leader used to do. Did you ever play Physics Jeopardy? Physical Science Jeopardy? One of our TA or one of our SI leaders used to do that for her reviews. So here's something that you might find to be a good study procedure. Write down a list of formulas that we have used, and then the Jeopardy answer.
I actually have a review sheet to write down the formulas on the SI side.
Okay. And Maria just told me she has a review sheet on the SI site for all the formulas. So yeah, you can fashion for studying a little game of Jeopardy. All right, last time we talked about Newton's laws of motion. The first one being actually Galileo's law, the law of inertia, that an object will remain in straight line motion at constant speed if there are no unbalanced forces, i.e. net force 0. We talked about Newton's second law, basically about the net force. F net equals ma. There's the vector version of it. Here's the scalar version, S-C-A-L-A-R, scalar. That means there's no direction in it. And so if you're just trying to figure out the size of a force, you could use that one. We talked about how to calculate it, how to sketch it. And the textbook gives you some sketching tips. The textbook goes over the whole idea of the parabola. When you have two force vectors that do not balance, and they're not in the same direction, they form a parabola. Or not a parabola, what did I say, parabola? Parallelogram, sorry. And that's in chapter 3. So here's a few different forms. Here's another form, m times delta v over delta t. And we're actually going to take that one next Tuesday and turn it into some interesting concepts concerning the symmetries that are built into space-time itself, the momentum and the energy of a dynamical system. Another thing, the special example, the weight force, it has its own formula. W equals mg. There's the scalar version of it. And let me just park that up here next to F equals ma, because it's a very frequently used version of F equals ma. And then the other thing we talked about was the metric unit of force, which is called the Newton, and it's equal to 1.00 kilogram meters per second squared. And everything in that is a fundamental unit. Kilogram is a fundamental unit of the metric system. Meter is a fundamental unit of the metric system. Second is a fundamental unit of the metric system. And actually, all that stuff is discussed in Chapter 1. And Newton is derived from distance measurements, mass measurements, and time measurements. Now, I'm not really sure what this little hound dog, I guess that's a dog. He's happy. He looks happy, right? I saw this on Reddit the other day. I have no explanation for it, but forces are going to help us render an explanation of acceleration and directionality. So let's get back to this. I want to emphasize we cannot observe a Newton of force. There's no, you can't go to Paris and go to the System International building and look at the International Newton inside of a bell jar, a glass bell jar on top of a little pedestal, and encircled by velvet ropes so that nobody touches it. It doesn't exist. It's derived by looking for accelerations and having mass measurements. So another thing that I want to review with you is that the presence of a force we detect by looking for accelerations in some way. If we find an acceleration, we know there's a net force. If we know there's a net force, we know that there's at least one force acting. And we got to try to analyze things and do experiments and figure out all the forces. The path through space that an object takes, it can have different kinds of accelerations, which hopefully we can measure. We've got, a path through space might be a curved path, and we're going to study those today in detail. So we have to know a lot of positions and a lot of times, a lot of time stamps. Straight line, we just need to know the beginning and the end, and a velocity, or a set of velocities. Things can speed up or slow down on any given path. And the other thing that can change is the the velocity's direction. So anytime you have a path that is curved, if something's following a curved path, then it is experiencing acceleration, even if it is on cruise control. If it's on cruise control and the speed's not changing, if the direction is changing, we would still say that there's an acceleration. All right? So you can also have a combination of speeding up and changing direction. So that's like hitting the gas as you go through a turn or you come out of a turn. Or 2 and 3, slowing down as you go into a turn. So slowing down as you change direction, you might want to do that as well. Okay? So going onto the interstate or getting off the interstate would be a combination of those two. Now we're going to talk about a baseball here. What I've got sketched out here is a baseball, and the mass of a regulation U.S. baseball is 145 grams, 0.145 kilograms. And the corresponding weight force for that is 1.421 newtons. And what I've done here is I put a dot up here to symbolize the center of mass of the baseball, and a little teeny arrow to, well, not a teeny one, a fairly good sized one, to represent the weight force. Now, we're going to talk about gravity and how gravity can change the direction of the velocity as well as speeding up and slowing down. Now, gravity is straight downward, and we know that it can cause a speed up or a slow down. But gravity can also cause a change in direction. And we're going to talk about a couple paths here for a baseball in a ballistic arc, two different kinds of ballistic arcs, or free fall trajectories, for which the change in velocity is featured and generated by the force of gravity, which is straight downward. Now let's keep going with number 3. The first trajectory that we're going to think about is the baseball pop-up. All right, straight up, come straight back down, and you gotta let the catcher catch it. You know, if you pop it up, you have to move and let the catcher catch that pop-up. So for a pop-up, the acceleration is always downward. And what that means is that delta V is downward. Right? If you're on the way up, your delta V is downward, negative. That means you're losing speed. So on the way up, that baseball is getting slower and slower. Right? And hopefully that appeals to your common sense. It slows down until it gets to the very top of its motion. Then it turns and starts coming back down. And so it regains all that speed on the way back down. Whatever speed it had upward at the very beginning, it has the same amount of speed but downward when it gets back to home plate. Now, if you have a base hit towards the outfield, now you've got some vertical velocity to start with and some horizontal velocity towards center field. All right, the acceleration is still straight downward. That hasn't changed. And it loses vertical speed on the way up, gains it back down, it gains back vertical speed on the way back down. But along the way, it retains all of whatever horizontal speed it started with. And why is that? The reason is there's no such thing as horizontal gravity. Gravity on the surface of the Earth is strictly downward. And for that reason, the delta V, the acceleration is downward, the delta V is downward, so the downward speed or the upward speed is going to change. Gravity is not horizontal, so there's no horizontal acceleration. Therefore, there's no horizontal delta V. And therefore, whatever you start with, horizontally speaking, is what you finish with. Now, we're going to sketch out both of these trajectories, starting with the pop-up. Okay, so I have my baseball up here, and I'm going to start my pop-up right down here. Here's a dashed line to represent the level where the ball leaves the baseball bat. Okay, so this may be about 3 feet up from the surface of the ball field. All right, and give it some upward velocity. All right. Now I want you to go about 3/4 of the way up to the baseball. All right, and about 3/4 of the way up, 1/4 still to go. It's down to about half that initial velocity. So make this arrow 3/4, kind of eyeball in 3/4 of the way up to your baseball, and then make the arrow half as big, kind of eyeball in, but it's still going upward. All right, so this is like 3B. It loses speed on the way up, the pop-up. and then it turns around. It's lost all the speed up at this level. And this is known as the turning point in the motion. In the turning point in the motion, you've lost all your vertical speed and you didn't start with any horizontal speed. So you're just kind of, at that instant of time, you're at rest. And then you start coming back down. So now, when you get back down to the same elevation, 1/4 of the way down, 3/4 of the way to go to get back to home plate, you've got back half your speed, but it's downward. All right, so this is 3C. It's regaining speed on the way down. By the time it gets back to home plate, you've regained all of that speed. Now, this is neglecting air resistance. Okay? If we were, an artillery team for the U.S. Army, we'd want to factor in air resistance. If we were, designing a rocket or designing an aircraft or even a car, we'd want to consider the aerodynamics. In other words, the air resistance. But for us guys here at UCF in physical science, we'll just forget about air resistance. All right? And I like to describe this process of losing speed on the way up and regaining speed on the way down. Just like that saying, the Lord giveth and the Lord taketh away. And here it is. The Lord is taketh thing away up here, and on the way back down, He's giveth thing back. All right, so you can think of it that way. The same thing happens if you have a base hit towards the outfield. Now, I have vertically exaggerated this one. So this is like a really towering fly ball. I mean, really towering. If this is center field over here at the far right, lower right here, then this point up here is like almost half a mile. So this is like an extremely high pop-up. All right, high fly ball. Anyways, go ahead and sketch in the baseline level where the free fall trajectory, the ballistic arc, starts. And go ahead and sketch in the top level, the maximum altitude. The fancy scientific name for this altitude is apogee. A-P-O-G-E-E. Apogee. And sometimes if you listen to the guys at NASA, at mission control, they'll say, well, Apollo mission is approaching apogee. Or Apollo mission is approaching perigee. Apogee is the farthest point on an orbit away from the Earth. Apo means away. And G is Greek for geo, Earth. So the farthest point away from Earth, that's this one up here. And the fancy name for it is apogee. All right. So let's say that this guy, he doesn't pop it straight up. He has a towering fly ball. And he starts with the same amount of vertical meters per second as the other guy. All right, so make this arrow the same size as this one over here for the pop-up. All right. Now, up here at this level, go ahead and sketch in another arrow, and this one's happening. So this 3/4 of the way up, and this arrow is half as big as the initial velocity arrow. This one down here in the lower left of the parabola is the initial velocity. This is time at an intermediate, this is the velocity at an intermediate time, or the vertical component of the velocity at an intermediate time. Now up here at apogee, zip, zap. There's no vertical meters per second up here. It's the top of its arc. But then when it comes back around, you're getting it all back. But it's downward speed. And then by the time it gets, now here's the center fielder catch. Just before it hits the center fielder's glove, it's got this many meters per second of downward speed. Now, there's something I haven't mentioned here in this diagram. What haven't I mentioned? Think. Direction, more than that. There's something more. There is something, direction, the answer has to do with direction. What? Go ahead. Did you have an idea? Yeah, the horizontal speed. We haven't drawn that. Let's throw that in. Go down here to the initial point. Start. And just kind of draw. Okay, and I backed out my dashed line there. Go ahead and draw in a little teeny. It doesn't need much, in my diagram anyways. This little teeny vector here to the right will get me to the outfield. And this vertical one will get me way up here into the stratosphere. All right. Over here, intermediate time on the way up. Yeah. Draw the very same size tiny arrow. And why is that? Because there's no such thing as horizontal gravity. So that part of the motion doesn't change. That component, there's no delta V in the horizontal direction. Right? Unless you're in a Bugs Bunny cartoon. Now, let's go up to apogee. What should I sketch in at apogee? Same arrow sideways. Dun, 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 dun. It's just pretty small in this diagram, but. So in this trajectory, look at what we got here. At the apogee, the velocity is horizontal. The acceleration is perpendicular to that. Nice. Now over here, at the intermediate point, the velocity is kind of at a slant, as we'll see in a minute, and the gravity is always downward, acceleration, but only at apogee is it perpendicular to the velocity. All right, let's go down here. All right, intermediate point on the way down, a fourth of the way down. On the way down, 3/4 of the way to go, and we still got a little teeny tiny bit of horizontal velocity. Next time I do this, I'll probably make it a full page so you can have a bigger horizontal velocity arrow. And the same thing down here. So the velocity vector down here where the center fielder, he doesn't want to just have his mitt horizontal. He wants to have just a little bit of tilt so that it's faced right into the direction of the, and that's a little bit tilted down here because he's got a little bit of horizontal velocity over here. So the idea here is that the direction of the velocity vector is changing continuously. Every instant of time, it's changing. And that's because the path has two components, one of which doesn't change, the horizontal, and the vertical component of the velocity, which does. And therefore, those two components, here's how they look. If you map out right here on the upward intermediate time, that's what the velocity vector would look like. It would kind of be slanted in this direction. So go ahead and I put my red fuzzy arrow over here to the left. I moved it a couple centimeters to the left just so you could see it. But really the tail of it should be right here on this dot where the baseball is. But I parked it over here to the left. And then similarly over here, same size arrow, but tilted at this, but it's downward now. All right. So this arrow here on the intermediate point on the way up, it's tilted a few degrees to the right. and it's pointing upward to the right. This one over here is pointed a few degrees away from horizontal, but it's pointing downward. So the tilt angles here are the same, but the orientation is upward for the first intermediate point and downward for the other intermediate point. All right, now we're going to do some more work with changing delta V and stuff like that. But is there a question back here? No questions? Okay. We're going to do some more with delta V and directions and curve path. But before we do that, I want to talk about Newton's third law, the law of action and reaction. Here's a great looking picture of Usain Bolt. What a guy. Question number 1. Is there a pair of skateboards in the lecture hall? Raise your hand if you have a skateboard with you today. 1. Oh, come on. Okay. In the back, bring your skateboard down, and you bring your skateboard down here to the front. And yay, we have 2 skateboarders. We had 3 in the previous class. Now I'm turning the lights up, but I'm going to narrate. This will be in the YouTube. Question? Yeah, come on up. All right. And I want you guys to stand up here in front. All right. Now, what is your name?
Michael.
Michael. And what is your name?
Isabel.
Isabel. Okay. Okay, and what is your name?
Alex.
Alex. Okay. Now, what we're going to do is, okay, Michael and Isabel, what I want you guys to do is put your skateboards down, and I want you to go toe to toe. Okay. So Isabel face to this side over here, and Michael, you face Isabel. Okay. And I want you to stand on your skateboard. All right. Now I want you to get toe to toe. Move forward a little bit there, Mike. Okay. All right. Now what we're gonna, and this is gonna look a little bit weird, but all we're gonna do is push off. Okay. So I want you guys to put your hands up like this. Yep. Don't push off yet. When I count it, when I say go, I want you to push off. Okay. Now Isabel, I want you to push, and Michael, I want you to push. Okay. All right. When I say go, 1, 2, 3, go. Whoa, what are you doing over there? Did you guys notice anything? She went further, yeah. Let's try Alex and Isabel. And Isabel, you move over to this side. Alex, you come over to this side. Let's see if it's like left-handed versus right-handed or something. Okay, so mount up. Okay, and get ready to push off. And when not yet.
Just getting my balance.
Okay, I don't want you to fall. Okay, when I say go, 1, 2, 3, go.
She just weighs less than I do.
Alex over here, Michael over here. Let's look at this combination. So everybody's getting 1 try on the left, 1 try on the right. Hey, let me ask you a question. Alex and Michael are going to push off. Now, which direction is Michael going to push? He's going to be pushing to the left. What direction is he going to move? What? If he's pushing to the left, how come he's moving to the right?
Because I'm pushing everything up.
Because Alex is pushing to the right. All right. All right, now go ahead and, when I say go. 1, 2, 3, go. Whoa. Notice anything about this?
They're receiving each other's equal force.
Yes. Sir Isaac. Yes, that's correct. They're both pushing with the same amount of force, but they don't look like They did the same thing. Right? Did you notice that? How would you... Well, let's keep going. Thanks. Let's give a hand for Alex, Isabel, and Michael. And let's keep going. Let's take some notes. Because what these guys have just done is give us a demonstration that will allow us to think about Sir Isaac Newton's law of action and reaction. The law of action and reaction, it's really a law about forces. Specifically, Alex pushing Michael. Michael pushing Isabel. And Isabel pushing Michael at the same time. When you push off, your opposite pushes you back. That's just the way nature works. And a good example is the two skateboarders. Last one we had Michael and Alex, and Michael was pushing Alex to the left over here, but for some reason he got pushed to the right by Alex. And those interaction forces, according to Sir Isaac Newton, are equal in size, but opposite in direction. Here's the law, one way to write it. Whenever two objects interact, like two skateboarders, the force exerted on one object is equal in size and opposite in direction to the force exerted on the other object. Okay? So let me rephrase this in terms of skateboards. Whenever two skateboarders interact, the force exerted on one skateboarder is equal to in size and opposite in direction to the force exerted on the other skateboarder. Let me repeat it. Whenever Alex and Michael interact, the force exerted on Michael is equal in size and opposite in direction to the force exerted on Alex. So they each get the same number of newtons. Go ahead and make a note of that. They each get the same number of newtons, except one's going to the left, one's going to the right. Now, the same thing applies to this football player, number 35, from the UCF squad a couple years ago. And if you look at this picture, you can see that he's kind of throwing his foot, his right foot. You can see this photo caught him on tippy toes, but he's throwing his right foot down and behind him. I mean, it's very similar motion to throwing a ball with your arm is what you do running. And if you've ever been on a track team and you do the sprint events, you may have heard your coach say to think of sprinting as throwing the track behind you. Now, here's the force that he is exerting, number 35, this black arrow. It's down into the ground, and it's kind of pointing aft behind him. All right? And according to Sir Isaac Newton's third law, that means that the ground is actually pushing on him with this yellow arrow. And the ground is pushing him up and forward. And he's getting the rigidity. If he were just standing, he'd get upward normal force. But because he's wearing cleats, he's digging into the turf a little bit, and he's actually able to get upward normal force from rigidity and also some down the field force toward the end zone, hopefully, from the turf. So away he goes, and he's heading for the end zone. Hopefully UCF gets another first down. Now, one thing I want to point out to you, if you think, Dr. B, the ground doesn't do anything, it's just sitting there, get out of town. No. That's like saying, Sir Isaac Newton, get out of town. It's no good. And here's how you can think about it. You couldn't get this to work if the field were made out of jello or if the field were made out of water, because there's no rigidity. There's not enough rigidity. And if you've ever noticed that, nobody ever plays football on a field made of jello. It just doesn't happen. And this is one of the reasons. Okay, because you've got to have some rigidity in order to get that push force. To get that yellow arrow here, you've got to have some pushback from rigidity of the surface that you're trying to run across. Another thing, you've got to have some grip. I mean, he's got cleats on, so he's getting a good grip into the turf. But if he were running in shoes that instead of having spikes, instead of having cleats on the bottom, if they had Teflon on the bottom, and if the field were made of ice, like an ice skating rink, he couldn't go anywhere because he couldn't get any friction between him and the surface. So you've got to have some rigidity of some kind and some kind of friction. Ditto for Usain Bolt and these guys running in the Olympics. This is down in Rio. I don't know what event this is. I think this is probably the 4x100 relay. Because see how they're all tilting to the left? I think that's what that is. His right shoulder is higher than his left shoulder, so he's just coming out of the curve. Anyway, in this case, it's his left foot pushing the track back, and the track pushes him forward to the finish line. Now here's another diagram. Think of an astronaut out in space. And out in space, there's not much, if you're far away from a planet or something like that, there's not much force. But if you're near a spacecraft, you might want to shove the spacecraft to the right, and then the astronaut's going to get shoved to the left. So this is what happens. Those guys up in the space station, they have to be tethered really carefully. And I've noticed that, like the space shuttle, they used to have them on the big Canada arm, and they'd kind of like on a crane, and they'd anchor their feet at the end of the Canada arm, and that would keep them in place so that they could push things and work with stuff. But if you're out in space and you push something, if you push something toward the mothership, you're going away from the mothership because of Newton's third law. Now, the thing about this example, that spaceship, that satellite is made of metal. And so it probably has a lot more kilograms than the astronaut. So they're probably not going to have identical recoil speeds. And we saw that with the skateboarders up here. Michael didn't get as much recoil speed as Alex or Isabel, right? And there's a reason for that. We're going to talk about that, the symmetry inherent in different states of motion between the skateboarders. So this guy over here doesn't get much recoil velocity. And this student on the right with the red skateboard gets quite a bit of rightward velocity. So we're going to tackle that next Tuesday. And we have an exam coming up Thursday. But over the weekend, we won't have any homework. Oh, by the way, student asked me, Dr. B, do we have lecture after the test? And the answer to that is N-O. No, we don't have test. Or we don't have lecture after the test. We just have a test. And believe you me, you're going to want, most of you are going to want every minute you can get to finish that test and to crush it. And that hopefully will be your attitude coming in. So we take the test Thursday, and then you turn it in up here at the front table, and then you're out of here. But if you want to read ahead, you can read ahead the skateboard example in chapter 4. Now, let's finish up a few more concepts in chapter 3, and this is page 38 or so. The previous discussion was actually past chapter. The third law is mentioned after uniform circular motion. But uniform circular motion concepts are starting approximately page 38. Now, this is an overhead view of the Nardo ring. It's a place called Nardo in Italy. And it's a circular test track that they built down there in the boot heel of Italy. Here's a picture of it. Nardo Technical Center. And it's kind of a cool place. They test experimental vehicles and stuff down there on that circular track. We'll get to that in a minute. Let's talk about curved trajectories in general. And as I mentioned before, if you're on a curved path, and even if you're at cruise control, if you're going through, like this path here, go ahead and pencil in a little curved path like that, something like mine. If you're going through that curved path at 20 miles an hour or something, you're still accelerating because there's going to be a change in the velocity arrow. You're changing directions. And that means that you have an acceleration vector. Therefore, it takes some net force. And the nature of that acceleration, the nature of that net force, is what we are going to talk about now. So what I want you to do, excuse me, kind of sleepy. Didn't get much sleep watching the game last night. At each point on the curve, there's a radius of curvature. So what I want you to do, go ahead and pick a point, any point on the curve. I put mine right here, kind of in the middle of this first turn, the right turn. And Alex, this other turn here, turn number 2, that's a left turn. If you think about it, you're turning to the left when you go through that second turn. The first turn, you turn to the right. So what I want to do is sketch the velocity vector at that point. And then after we get the velocity vector, we're going to draw in the radius of curvature. And I'll show you how to do that. But first, let's get the velocity vector. The velocity vector is always tangent to the path. So draw on a tangent line. The tangent line is a straight line that just gracefully touches at this one point only. It doesn't poke through the curved path. It just kind of grazes at the top. Touch and go. 1 point and 1 point only. All right, so mine that looks like a pretty good tangent line. Do the best you can. Now, if I'm moving from left to right, my velocity vector is going to be in this direction. Now, if you have your tangent line, look what I do now. Look at my velocity vector. Here it comes. All right, there's my velocity vector. And so just give it a good size arrow. It doesn't have to be any particular size. But it does have to be oriented tangent to the path. In the theory of relativity, in curved spacetime, we use this idea of a tangent vector all over the place. So this is a pretty powerful concept here. Tangent vector to a path. All right, now let me get my vector v labeled. And I can erase my tangent line. You can keep yours if you want. It's done its job. And let me move this thing out of the way. Now, at each point, there's a radius of curvature. And I want you to see what I do. Now, don't sketch this in until I tell you to sketch it in. I want you to eyeball it first. Okay, so eyes forward for just a minute. I'm going to draw in a circle that just barely touches at this same point. Here it is. All right, now I set it just a little bit to the side. And the idea is, for at least a short distance, this imaginary circle is right along the actual path. All right, so let me move that circle right onto the path. It's a couple millimeters away now. Down and to the right. Now let me bring it right in there. Okay, now watch what I do here. Eyeballs up. All right, there it is. All right. And so that's the circle that matches the path, if only for a short distance, a few meters. If this were the path of an electron, we might say, oh, for a few nanometers. But for whatever distance it is, it matches just for that small neighborhood right by that point that we're trying to study. And notice that I've got 4 radii, one of which goes from the center of this circle to the point under consideration. So the tail of my velocity vector is at this dot right here on the curve, and my radius, this radius, the one that's kind of going northwest, is also attached to that point. So the center of the imaginary circle is inside the turn. Here it is. There's the center of the circle. I've got 4 radii. They're all perpendicular. All right? And so they meet at the center, as radii do. And one more thing. If the circle matches the path for a few meters, a few meters before and a few meters after that point, then it means that the velocity vector is also tangent to the circle. It's tangent to the path by definition, and it's also tangent to the circle, right? At that point only. Now, if you go to a different point, down here in turn 2, you need a different circle, smaller circle. Down here in turn 2, the center of curvature would be to the left of the path. Because you're making a left turn, right, over here in turn 2. But in turn 1, at this point, yeah, pretty much right there. Comment number 3. If we had an exactly circular path, and this one that we've got here is just kind of a squiggly general path, nothing, no pattern to it. But if we did have a perfect circular path, then that path would have 1 radius of curvature. That's it. That's what defines a circle. Every point on a circle is the same distance away, and that distance is known as the radius. Now, I want to talk about the net force on this general curved path. Number 4, if we're on cruise control, if we keep the speedometer constant, in other words, we drive the entire path, for instance, at 10 miles per hour, nice and smooth, nothing but net, then the acceleration is perpendicular to the velocity. And why do we say that? If the speedometer is constant, you're not getting speed up. So there's no meters per second squared of acceleration in the direction of the velocity. And there's no meters per second squared opposite the direction of the velocity, so it's not slowing down. That means the only way you can have it is exactly perpendicular to the velocity. Your acceleration is perpendicular to the velocity. Okay? So there's no slow up, you're just changing the direction. And what that means is that the acceleration is along the imaginary radius of curvature at that point. And it points directly to the inside of the turn, directly to the center. And that, my wonderful students, is why we call this acceleration a centripetal acceleration. Centripetal means centri, center. Petal means toward. It's like some Greek word. It doesn't have any English, cousin words, any English cognates. But centripetal means toward the center. Centrifugal. Centrifugal means centri, center, fugal, fugue, fugitive, flee. Centrifugal means to flee the center, to direct itself away from the center. We haven't got that. This is not a centrifugal acceleration, and it's not produced by a centrifugal force. So I want you to write the word centrifugal. I'll spell it for you one more time. C-E-N-T-R-I-F-U-G-A-L, centrifugal. Write that word down and then put a line through it. Because this is not centrifugal. It's centripetal. And this acceleration changes only the direction of the velocity. And it's kind of interesting. If you think about that baseball, the one point at which there's acceleration perpendicular to the velocity, purely centripetal acceleration, is the apogee. Now, this acceleration at this point, you might need a lot of net force or a small amount of net force, depending on, first of all, how fast you're taking the turn. If you're taking the turn too fast, your tires might not have enough grip, and off you go into a snowdrift. Also depends on the tightness of the curve, the radius of curvature. The smaller the radius of curvature, the more grip you need on your tires. Same thing. If you try to take it at 20 miles an hour and the curvature radius is too small, you're going to... And I saw somebody out here on University one day. I was coming out, and I think it was this guy, he piled up his little Nissan into a telephone pole right by, you know, where you turn off to those new apartments. What's the name of that place? Where they have that, you know, the corner where McDonald's is and yeah, the plaza. Okay, so it was before the plaza. It used to be a shopping center there. And so this guy, there's an entrance to the shopping plaza, and right next to the entrance was this big telephone pole. This guy he ran right into it. And I don't know if it's because he had bad tires, but in any case, if you're trying to make a tight curve, better slow down because you need net force toward the center of the turn. So look at these tires. Which one is going to be better for going around a tight corner? Well, the one on the left. It's got more tread. This other one is like a banana peel, just about. Forget about it. You do that, you know, you're asking for trouble. Now, let's take a look at the Nardo ring. Here's another, this is Google Earth. I love using Google Earth. Here comes the Nardo ring. Closer and closer. Closer, and here it is overhead. Now the Nardo ring, talking about force and velocity and curvature, the outermost lane is banked so that at 149 miles an hour, you don't have to turn the steering wheel. They could have a robot driving the car straight ahead. If you go faster, you have to put a little bit of crank on your steering wheel. Get a little more grip from your tires. The innermost lane is banked differently, and it's set for testing trucks at 50 miles an hour. So if you want to go faster than 50 on the Nardo ring, on the inner ring, you have to crank the steering wheel a degree or two. Now, so that's the Nardo ring, and you can read more about the Nardo ring in the textbook. I want to derive now two equations on a simple circular path like the Nardo ring. And make a note, this term, uniform circular motion, what that means is an object is moving along a perfect circle and constant speed. So uniform circular motion means circular path, cruise control, constant speed. Now what we're going to do is look at the position and the velocity of an object in uniform circular motion at two different instances of times. So here's the circle, the position, radius r, and then the velocity pointing straight up. The position vector in black, marked with the letter R here, is at 3 o'clock. And for that reason, in uniform circular motion, the velocity vector is perpendicular to that, and it's going straight up. Now, a small amount of time later, time t2, the position vector r has changed. So now you're at about 2 o'clock. And so the velocity vector is tilted 30 degrees to the left. 2 o'clock is 30 degrees up from 3 o'clock. And the velocity vector is 30 degrees to the left of being perfectly straight up. Now, we're going to try to take apart and analyze these two circles. So what I want you to do is take first the two position radii and form a triangle with them. Here's what I mean. Look what I'm doing here. I take this second position radius and I kind of park it over here. All right, so there's its geometric relationship to the first position radius. And then what I'm going to do is I'm going to move it over here to the lower left. And you put it wherever you want. And so kind of copy those two so that the tail of each is at the same point. Right? So you have like a 30-degree angle there. And just park it somewhere on your page where you have a little bit of room to sketch. Now we're going to do the same thing with the velocity vectors. This one's upward, straight upward. This one's tilted at time t2. It's tilted 30 degrees to the left. So again, we're going to copy. There's my two copies. And then kind of move it over here to the upper right. All right. And now I'm going to move my two circles, and shrink them down and move them to the upper right. So down here is my position triangle. These two are the same length. Now I want you to draw in the third side. Here it is. This dashed line. All right. And go ahead and mark R and R for the two solid lines. And hey, you guys, what kind of a triangle is that? Isosceles. Remember that? I-S-O-S-C-E-L-E-S. Isosceles. This dashed line is the approximate distance that the object travels. Now, I say it's approximate because it's traveling on a circle. And this is straight across. This is a line segment. But it's pretty close to the path of the circle. Now, go over here to your velocity arrows. They're tail to tail. And let's connect the third side and another right triangle. And the sides, the isosceles sides, are V and V. Uniform circular motion means cruise control, so V and V. Circular motion means R and R, no matter what two times I select. Now, let me ask you a question. This, in the position triangle, the base, the dashed line of the position triangle is the approximate distance. All right. What's this base up here for the velocity triangle? Yes. Change in direction? Incorrect. Actually, I shouldn't say it's related to the change in direction. It's a change, though. What do you think it is? It is parallel to the acceleration, but that vector itself is not the acceleration. And we're going to get an acceleration from it in just a minute. By the way, did you get your wallet?
Yeah.
Good. This dashed line for the velocity triangle. What do you think it is? What should we call it? Any more guesses? Horizontal what? Horizontal speed? No. Yes. Net force? No, it's not net force, but it's going to be parallel to the net force because this is delta V. All right, now you guys are all tippy-toeing around it, but to be precise, this is delta V. Now, these two triangles are going to get us an equation for the acceleration. Because they are similar, the angles are equal, and the sides are proportional. So if I make a ratio of the two isosceles sides, one from the position, one from the speed triangle, I could take and equal it to a quotient of the bases, the base of the position to the base of the speed triangle. So this is pretty much key right here. This distance, V delta t, and we're going to use that. So we're not going to have distance d there. We're going to have V delta t. Now let's put together the proportion. Here it is. The left-hand quotient, R over V, is the ratio of isosceles side on the position triangle to the isosceles side, or the long side, of the velocity triangle. And then the right-hand side, this quotient on the right-hand side of the proportion is the base of the position triangle on top and the base, delta V, of the velocity triangle on the bottom, in the denominator. And that proportion is the key that unlocks the formula. If we've done everything right, then this proportion is righteous. Now, just to reemphasize, these are the isosceles side, the long sides of these two triangles in the order position over speed. And then over here, the right-hand quotient, that's the isosceles base in the order position over speed. Now, does anybody see an acceleration in there? You know, kind of like cleverly disguised. An acceleration. Do you see it? Can you see an acceleration? What do you see? The top of what? Top of the fraction? That's a delta t and a v over here. That's the numerator of the fraction on the right. Anybody see an acceleration? What do you see? Inverse of the acceleration formula? Huh? All right, it's a flip-flop. Look at this. I got delta t over delta v. That's the flip-flop of the acceleration. Looking good here. So here we go. Let's flip-flop it. And let's get this v. We'll flip-flop it and park this v and this v together on the left, and then flip-flop everything. And what you get is delta v over delta t, acceleration, and v squared over r. And that, my wonderful students, that is the centripetal acceleration. There's the formula. A subscript C is equal to V squared over R. F subscript C, centripetal force, that's just F equals ma. Now next week, we're going to apply this to universal gravitation. But Thursday we have an exam. You're dismissed. It's 1:20. Get your homework started, and I'll see you on Thursday. You're dismissed.